Okay, welcome everybody. My name is Benjamin DeBow, and I'll be talking to you a little bit about our offering with InterSystems IRIS for scalability, for scaling up and scaling out. I'm between you and probably the bar or drinks or any form of it, so I hope, no, the closing keynote. Anyhow, so I'll try to kind of make this informative yet pleasant. If you have any questions, don't hesitate to ask them during the session. We've got some time for Q&A at the end because the demo is going to blow up anyhow, and we're going to. Well, so if you have questions, just don't hesitate to shout. Maybe first, a little bit of questions for you. Who amongst you has already been playing around with Iris a little bit? And who's already taken a closer look at the sharding functionality? Perfect. Cool. Okay. So, what are we going to talk about? We're first going to talk a little bit about what do we mean with scalability, what are, well, just get some definitions in place. We'll define through pictures, so that works. Then I'll talk you through our new and updated architecture for sharding. So the people who have looked at sharding in the 18.1 release will still recognize plenty of it, but you'll see that we've kind of evolved and we've made things a lot easier for people who want to adopt this. And then I'll talk through our roadmap with InterSystems IRIS when it comes to scalability. What do we have in stock? What can you expect to see in the coming features and the coming releases? And then after that, I'll have a demo or leftovers of a demo because I messed something up just before. And I don't know how it's going to go, but I'm sure it will be good and fast, and you'll love it. And otherwise, we'll just go and have a drink and forget about it. So when we say scalable, you could say, oh yeah, that's one of the four words in the InterSystems design philosophy, and that's true. But you can't look at these words in isolation. We can't talk about scalability in isolation because if your system all by itself scales fine, well, that's good for you. But if your system is not able to talk to other systems, so if it's not interoperable, your scalability is going to be like a pinnacle that rises very high and might be very impressive, but you can't really connect to other sources necessarily. So you still have to abide by standards such as SQL while you're doing the scalability thing. It obviously has to be intuitive, so you want to make sure that people can easily scale. And it has to be reliable for sure. So anyhow, just wanted to say that we don't look at scalability in isolation. We really want that to be part of this mix, this sort of indivisible forward design philosophy. So let's take a look at what scalability really is about. Why is scalability important? Scalability is, of course, fun. It's fun to be able to say that you can sustain very heavy workloads by adding more resources, but it's not just enough to be able to support, to be able to run on a system that uses a lot of CPU cores or that is able to use a lot of memory. The challenge is making sure that they are used effectively, that you have sort of linear scaling, that the money you put into it is also going to come out again in terms of processing power, in terms of efficiencies. So in that sense, it's really about cost efficiency. And it's important to not just kind of simplify that to cost efficiency when you're growing, but you can also look at it as the sort of static cost efficiency when you're initializing your system a first time, when you're kind of sizing your system for the first installment. If you are then able to quite precisely say, I need this much hardware in order to sustain the user workload that I'm anticipating, that's also cost effectiveness. That's cost effectiveness thanks to scalability. And then being able to, still in a cost-effective way, scale when your user workload or your data volume increases, that's the other part of scalability. So scalability is not always the dynamic thing, but it also applies to the sizing, the initial sizing. I'll be talking a little more about that tomorrow in my session about reference architectures. So why scalability is also becoming more and more important? Because the prevalence of cloud infrastructure makes this much more pronounced. Previously, if you wanted cost-effectively, to size your environment in a cost-effective fashion, you would look in the catalog of your hardware vendor and you could see a number of options. Now you can look in a ton of different catalogs of these cloud vendors, and they all have very varying instance sizes to play with. So you have a lot more flexibility to size your environment very specifically to the user workload that you're anticipating by just choosing from the very long menu on AWS or Azure or GCP of the systems that you want to use. And also for that, beyond that initial sizing, if you want to scale up in the dynamic version of scalability, it's easy to add these different nodes. You just spin them up. It's just a couple of mouse clicks or a run of the InterSystems Cloud Manager. So thanks to cloud, it's becoming even more beneficial to have a very scalable product because you can really size and really be cost effective to support the users that you want to support. So all of that context puts some pressure, obviously, on the data management software. Data management software needs to be able to get the most out of things. And while getting the most out of things, it preferably does so in a way that doesn't impact the users, that doesn't impact the applications that are written on top of the data management size. So a lot of exciting ways of looking at scalability and some exciting challenges for us as a database vendor. So now let's try and kind of find a different way of picturing the difference between vertical scaling and horizontal scaling. So scaling up means getting bigger, means swapping out what you have with something bigger. So if you imagine that you're you're working in dairy and you want to produce more milk. So you go to your cattle vendor and you ask, do you have a bigger cow? And then he can probably sell you a bigger cow. That's vertical scalability. That's scaling up. That's increasing the size of your singular resource. At a certain moment, your cattle vendor will say, sir, you already have the biggest cow I have in stock, but I can sell you multiple cows that together can give you more milk and can sustain your milk requirements. That is scaling out. But as you can see, scaling up, you can still do with the same machinery. Scaling out might require a little more specialized machinery in order to efficiently leverage the multitude of servers, the multitude of resources that you're putting into practice. So that's kind of vertical scalability, scaling up, and horizontal scalability, scaling out, as two different ways of approaching the can you produce more milk question. So we'll first look very briefly at vertical scalability and then take a much longer time to zoom into what horizontal scalability has in stock. So vertical scalability, again, means adding more resources to your server. You have one server and you just add a lot of CPUs to it, or you add a lot of memory to it. How can we leverage that? Parallel SQL execution is something that has been around since 2016 with InterSystems Cache. That works quite well. But in 2016, you still had to kind of tell the SQL optimizer to switch it on. You got to choose the queries for which you think it performs well, and then we would do it. By now, we have collected enough heuristics from real-world applications, etc., to kind of make that decision for you. So now, from InterSystems IRIS 2018.1, we will automatically parallelize all queries for which we know that it makes sense, unless you tell us not to. And if you tell us not to, please come and tell us why, because we have some pretty exhaustive tests on from which we derive the heuristics for which we make these decisions. So we're really eager to learn where we missed a particular mode of operation. So that's going to be something really, really interesting for 2018.02 because it's completely transparent. You don't have to do anything and you'll benefit from this. In 2019.1, we'll also, on the usability side, make sure that you can see all these parallel subqueries in show plan. So if you're into debugging or just analyzing out of curiosity what's happening, we'll have a lot more. And this is not the only thing that we're adding in 19.1 on that front. So that's for SQL. If you're more into just object script programming, the work queue manager is your friend when it comes to scaling up. The work queue manager is a very nice API in object script to kind of job off different processes that will do chunks of work, and you can then just wait until all of your processes have finished. You could model that by hand by using the job command, but that's very error prone, and I've triggered quite a few jobs that just ran for eternity. They're not still running, I did kill them. But the work queue manager really solves a lot of those, takes care of a lot of that complexity for you. So it's a really nice thing, and we're eating our own dog food. The SQL parallel execution is built on top of the work queue manager. Our BIQ builds are built on top of the work queue manager. I know domain builds are built on top of the work queue manager. So that's vertical scalability. But now, why is horizontal scalability becoming so much more important? So the vertical scalability is very important for doing the initial sizing, for doing that sort of static scalability scenario that I mentioned in the beginning. But it's very hard to vertically anticipate growth. You can, to a certain extent, you can add more memory into an existing server. You can sometimes add more CPUs into an existing server, but that's not very practical. So and also, if you want to scale up to that really big cow is probably going to be a fairly more expensive type of cow than the smaller ones. So when you get closer to the ceiling of what you can achieve with vertical scalability, the price of the components also goes up. Premium hardware comes at a premium price. So that's yet another reason why you can consider looking at horizontal scalability. And then the cloud economics obviously kind of make this even more pronounced and kind of add to it. So let's take a closer look at how our architecture, how our horizontally scalable architecture looks with InterSystems IRIS. So first, I wanted to start with design principles. And this is not like a retrospective of this is how we set about developing this architecture. This is really how we believe that also people who are adopting our technology should look at their cluster. It should be simple, it should be transparent, and it should be efficient. And if you are building a cluster, it should be simple for you to add more nodes. And you don't have to worry about setup or configuration or making sure that the configurations are exactly the same as they are in the other instances. That should be taken care of for you. It should be transparent for your applications. Your applications shouldn't care whether there's a 4-node cluster or a 10-node cluster or a 50-node cluster running underneath. That should be transparent. And it should be efficient, playing into the cost effectiveness thing, making sure that you get very good performance out of the box. And if you add more resources, we'll make use of them in the most efficient fashion, because that's what you're used from us. So how does that look? Building a scalable cluster. So I've got a certain data set, and I have an application that's sitting on top that's connecting into my database through JDBC, ODBC, who knows. And at a certain moment in time, it's time to grow. My data set has grown. I need to scale out. So I add a node. You just add another data node, and the data will be transparently spread across those two servers, and your clients can connect to any of those servers, and they will see the data as one logical union. They shouldn't worry about, they can just see it anyhow. And so probably you will put a simple load balancer in front of between those clients, so that it automatically spreads the workload across. And if you want to grow a little more, you just add more data nodes. There's a single node type, just data nodes. You point them to another node that's already part of the cluster, and it will just copy the configuration from that node that you pointed it to and attach itself to the cluster and configure itself, ready to take in data. Data will be spread across all of the nodes for new data that's inserted, and if you want, you can rebalance the data automatically across all of the nodes that you have available. If the demo works, I'll show it to you later on. And clients can connect to any node they want, and they will see the data as if it all were local. And we take care of getting the data from the place it resides to satisfy your queries. Now, if you do leverage one of our drivers, our smart tools, like the InterSystems IRIS connector or our JDBC driver, we will make sure that when we can, we will kind of transparently delegate some work already to the individual nodes. So for example, when you're inserting through the JDBC driver, we will automatically parallelize the insertion work to run against the nodes in parallel. So that's how easy it is to scale an InterSystems IRIS sharded cluster. Sometimes that's not even enough. Sometimes you need more speed. Sometimes you have very high data volumes and very high and very low latency requirements that you might not be able to meet with the layout that I just presented. In those cases, you can add a second node type, and only in those cases will you need another node type than the simple data nodes that we presented. And those compute nodes, they will act as a caching layer, sitting in front of your data nodes and satisfying the select queries. And all of the other queries will be wired transparently to the data nodes and operate on the data over there. And if you want, you can add more. You can just add more compute nodes. And again, adding a compute node means you point it to an existing cluster, to an existing node in the cluster, and it will configure itself using the configuration it just steals from the existing node. So that's how you can scale to serve these very high, very demanding workloads. And the proof of concepts that Carlos was talking about earlier this morning on Wall Street, they were using a topology like this, including those compute nodes. So that's it. That's building a fast and scalable cluster with InterSystems IRIS. So with that in mind, with that architectural picture in mind, let's take a closer look at what our roadmap looks like. So today, meaning 2018-1, tomorrow, meaning the 2019-1 release, which we're sort of in the process of finalizing at a code level. And then beyond 19.1 is kind of to 2020, etc. So how did we start? We started with the guys that Carlos was talking about on Wall Street. So we knew that these people were looking for a horizontally scalable solution that supported very large data sets. So that's 2-3 years ago when we started to build this sharding capability, and when we were really looking at it from an engineering point of view, with a focus on overall system performance, getting the most out of your system, and making sure that we get all of the fundamental engineering right, so that we can meet these SLAs, we can meet these performance requirements that these customers have. And we're going to meet them for the SQL scenarios that were presented to us in the first place. So that's the basic scale out and the basic SQL that we implemented in the first round. Now that we know we got those things right, and we've in the meantime been able to validate that at a couple of other sites. For example, LibIT, you might have attended the session that they presented over lunch. They adopted IRIS, they're using our sharding capability, and they were very happy with it and were able to transparently take advantage of it. So what we're now focusing on for 2019 is kind of getting that simplicity in the picture. So in the 18.1 release, we were talking about the sort of low-level fundamental roles in the architecture. Now, based on the experience we have from multiple customers, we're able to provide this more easy-to-use APIs and configuration modes that I just explained in the previous section. So also removing some of the limitations that were in place in the initial release. So there's no more restrictions on when you can add shards. You can always add shards. There's no restrictions on your schema. You can use all of you can use practically all of the SQL features that you might have been used to from before. So that's been our focus, to get that simplicity, transparency, and efficiency all up to speed in the 19.1 release. And then beyond that, we're gonna invest in even more elasticity. So being able to take nodes out of your cluster if you need to scale down for some reason. Look at other data models. We're making some good progress on supporting the object model, which is the second one that we'll be supporting. But there's a lot more out there. There's our multidimensional cubes. There's the document data model. There's what we can do with NLP. That's also sort of a semi-data model. So those are other things that we're interested in. So now for the system and the application level, let's zoom in on a couple of particular examples, particular features that are new or very close to getting released. So first, new in 19.1 will be support in our system management portal. Because 2018.1 was, let's say, an engineering release, we also had an engineering API, so an object script API that allowed you to make the configurations. Logical next step is making sure that people can also do that graphically through an interface. This is sort of also a prelude for a more comprehensive cluster management solution, but this is what we already get in place for 19.1. Another also extremely important capability that's going to be new in the imminent 2018.2 release is support for backups of a sharded cluster that are coordinated. Because backups are something that you take per instance. There's no way around it. You can't, you could map all of your storage to the same physical device and then take a backup of that physical device, but that's not very practical in the horizontal scaling story. So in 18.2, we're introducing an API that allows you to make sure that you can coordinate backups being taken across your cluster. And there's actually 3 ways that I'm going to briefly zoom in on. So the first mode is the Quiesce Resume. So with Quiesce, you're just telling your machine, stop, I'm going to create a backup. When you Quiesce, your write daemons will stop, your journaling will stop, your application will be unavailable for the duration of your process. Which also means that the moment when Quiesce finishes, all of your nodes in your cluster are at the same logical point in time. So you can take your backups. You probably want to do that pretty quickly. And by the time you're done with them, you can resume your system and it will resume operations. And you've got backups of all your system that together correspond to a logical point in time. So that's the one extreme. Pretty harsh because you have application downtime. At the other end, there's also a zero downtime alternative. This is the other extreme. You can do what you want. You can take backups of all of your instances at the time you prefer. You can even have different schedules for every node if you want. You just got to make sure that every now and then you create what we call a journal checkpoint, a coordinated journal checkpoint. What that means is that you issue the journal checkpoint command, and for a extremely brief period of time, your system will pause. It will roll to a next, or it will switch to a new journal file on every instance in your cluster, and then it will resume again. That's typically in the span of a microsecond or of a millisecond or something along those lines. So your application won't notice. But what that means is that this method will also return to you the names of the last journal files for every instance that participates in the cluster, so that if you make sure that you keep them all up to that point, you can roll back to the most recent journal checkpoint on all the individual instances, meaning that you will have again restored your cluster into a fully to the same logical point of time. And then the third scenario is a little bit in between. The freeze and thaw scenario is where you freeze your system, at which moment your write daemons will stop functioning. Well, intentionally will stop, and but your application can continue to work because your application will just write to journal files. In the meantime, we've also created the coordinated journal checkpoint, so we know up to what point you need to roll back. So this is a little bit in between the two other ones, but also works fairly straightforward. So that's the kind of coordinated backup feature that we're introducing with 18.2. Very important, of course, to make sure that these sharded clusters don't only work nicely in the lab, but are also can also be used reliably in production scenarios, because that plays into the kind of IRIS thing that I mentioned at the beginning. We don't look at scalability in isolation. And then the third thing that I wanted to call out as new features in 19.1 or in the imminent release is that we're removing constraints on scaling out. We had some pragmatic choices, some conservative choices in the initial release, but now we're making it possible to just add nodes whenever you like. And as soon as you add one, you can rebalance the data across the nodes so that you get again a more even distribution across the nodes in your cluster, so that also the work can get distributed more evenly across the nodes you've added to your cluster. So that's sort of a maintenance operation. So for now, we call it offline rebalancing because you can't query the tables while the rebalancing operation is running. But it's fairly robust in the sense that you can time box it. You can tell it run at most 10 minutes, and then resume normal work. And then we'll just in the next maintenance window pick up where it left and give you and continue rebalancing. And eventually it will converge to a more even distribution, or the most even distribution of your data. So actually all relatively straightforward things, but they really make this nice and elastic. In 2019.2 or 3, we hope to kind of remove the word offline and replace it with the word online. We already know how we want to do. It's just a matter of getting to it and getting into the release cycle. So that's sort of the another couple of points on the system level roadmap. So the full elasticity, so online rebalancing. The primitives we're putting in place for rebalancing will also allow removing nodes from the cluster if that ever becomes a requirement. Support for disaster recovery scenarios. That is again something that's that we currently left out of scope, but we already have high availability through synchronous mirroring, but having support for DR through asynchronous mirroring is something that's also on the roadmap. Rolling upgrades, being able to gradually upgrade your cluster rather than having to upgrade it all at once is also something that we want to look at in the longer run. Yes, Ted?
Can you say something about transactionality for inserts?
Transactionality for inserts. So if you're what we're not developing is full cross-shard transactions. There is no short-term solution for it that we are able to deliver. What we have been looking into and are actively looking for feedback on is sort of intra-shard transactions. So if your schema is built in such a way that the tables that participate in a transaction are co-sharded, which means that related data is stored on the same shard, we are looking into ways how we can provide you hooks to fit that into transactions. That's likely gonna work fine. That's also how many other solutions that say we have distributed transactions, how they deal with it. I believe it's also how Google Spanner does it. So it just puts, I wouldn't say constraints, but it just adds to your thinking when you're designing your schema. If you look at another customer of ours that has already been sort of implementing their own sharding mechanism 10 years ago, they built it that way. They just made sure that data that belongs together is stored on the same shard, and therefore transactions on that shard are guaranteed to be 100% consistent. But thanks for bringing it up, so I can admit why I use the term coordinated backup and not consistent backup, because, well, across shards we don't do transactions. And if you read small print for other vendors, you'll find out that there's very few that do it any other way. Okay, we're scaling up. We're going up to the application level, so got a nicely elastically scalable system level. So now let's look at what the application level has in stock in the upcoming releases. So co-sharding for any table. I already just described what co-sharding is about. So co-sharding is making sure that tables that contain related data, for example, based on a foreign key or anything, are actually stored, related data is stored together. So if you have a patient table and an encounter table, that the encounters for a given patient are all stored on the same shard. Because if you do it, if you can ensure that through your schema design, it can make a tremendous difference when you're joining those tables together. Because it means that by your schema definition, data that needs to be joined is all guaranteed to be on the same shard. So you can fully parallelize that join. And that can really make a huge difference for performance. So there were some limitations on, previously you had to explicitly define your shard key on all tables that needed to be co-sharded. Now in 2019-1, you'll be able to co-shard with another table and just point to another table and piggyback on that table's bucket distribution schema. So bucket distribution is how your buckets of data are distributed across the shards. So we'll see that in the demo as well. That part of the demo, I'm quite sure, will still work. Another nice feature with 18.2 that's coming up is the bulk loader. The bulk loader is a simple Java app that takes a properties file with a couple of parameters. You point it to a JDBC or CSV data source. You point it to the IRIS instance that you want to load into, and it will just pump the data across as fast as it can. It will use parallelized JDBC inserts if you're talking to a sharded cluster. It will use XCP if it's a non-sharded system that's with the schema supporting XCP. So it really goes pretty fast. So in another demo I did earlier today, we're loading 500K records in less than 2 seconds. So on my humble laptop. So how do those parameter files look like? Well, we'll see one in action in a minute or so. Another very important feature that we're going to introduce and show is sharded class definitions. So in 18.1, in our engineering release, we supported creating sharded tables through DDL, through data definition language from a SQL prompt or SQL application. That was because the scenarios that we targeted in that initial release were fully SQL-based, so that makes a lot of sense. But it was also a very convenient way for us to restrict the wealth of features that InterSystems IRIS has for object development, so that we could restrict what we needed to support in the very first release for sharding to only what you could achieve with DDL. Now we're going to open the floodgates and allow you to just use a simple keyword in the class definition that says this class is going to be sharded. And we're going to gradually add support for all of the other wonderful object features that are available in class definitions. So that's going to be that's a very interesting opening up a lot of capabilities. So an example of how that looks like is this is a very simple class, and there's no real requirement other than putting the sharded equals 1. So the use extent set is just there for educational purposes, because that should be the default for anything new going forward, but it's not a dependency for sharding. And then a slightly more complex class definition. So this is an encounter table that is co-sharded with our patient table that we had right before. So that's where you're saying that that the patient field is going to be used as the shard key, and it's going to be piggybacking on the bucket distribution of our patient table. Longer term, beyond these wonderful things, are support for other data models. So we're already getting a long way for objects, but it won't be part of the 19.1 release entirely yet. And then there's all these other wonderful data models that we're looking to support next. Workload distribution is actually a very interesting thing because it's sort of the other half of supporting the object model. So being able to support class definitions and support the %new and %save on a sharded class, that's one thing, but that will still run on the node you're connecting to. So with workload distribution, we want to give you an API to support jobbing off work to the other nodes in your cluster. So there's two main APIs that we want to support. One is an extension of the existing work queue manager that allows you to just send work to all of the different data nodes so that it runs on each data node once. And the other one is sort of a map function, a bit like the JavaScript map function or the Scala map function, or even MapReduce if you wish. So that's going to be part of a persistent class interface. So that means that you can apply a method to every instance of that class, and that will make sure that it runs on the data node where the corresponding record is stored, which you can obviously filter down to only a subset of your data set. So that's what we have in stock for workload distribution. And then expanding to other platform areas. So for example, looking at how we can make our interoperability capabilities also scale in the same flexible and smooth manner. And with that, it's time to start taking some risks and get to the demo. I'll try to save my back and do this from here. So first, I'm going to make sure that you can see something. So I actually had two parts and I messed up, so they all look as one now. But what I wanted to show you first is, so this is my little sharded cluster. I used the sort of cheat mode in which you can work with an individual instance rather than separate nodes. So, but that's just because I have only one laptop and I didn't want to carry 5 with me. No, of course you could do all that with containers, but well, this isn't the container session. So I've got a mixed set of shards, and I will create a sharded table into that. So let's create a class. This is all not spectacular because this is all technical stuff, but because we're in the Solution Developer Conference, I'm entitled to do this sort of thing. So we're going to create a persistent class. We're going to call it patient, and then I'm going to avoid creating typos that I don't have to by copying and pasting our little class definition. So here I'm using this new 19.1 feature using sharded classes. So if I compile, Atelier will push that to my, one error. This is never given an error. Of course, I need to point my project to, hell. Okay, so we start from a blank project. We point it to our server. I reinstalled the server this afternoon, and that was not the brightest ID. And I'm going to connect to my main namespace. And in that namespace, I'm going to create a class. It's going to be persistent. So, and if I compile it, it will push it to the server and create the class for me. So no data in there. It generates a bunch of internal details that we shouldn't worry too much about. But essentially, we've got our first sharded class, and we define through class definition language rather than data definition language, rather than DDL. So, oops, I'm gonna add our encounter table to it as well. And so from this one, so here I have my, so the foreign key relationship, you don't have to, it's not mandatory to have that explicitly. The only thing that's important is here, this co-sharded with keyword, but I could as well just get rid of this one if I wanted to. So much for the little atelier demo, but on the SQL side, I now have my sharded table. So if I go and look here, so I have my patient. Didn't it push? What's wrong here? Come on. So there we go. So here you can also see the shard key for patient is its ID. We just set that it should take care of sharding itself. And here for the encounter one is co-sharded with our patient table. And I can see that in my 6 shards, I have 0 rows each. So now let's add some data to it. And we're gonna do that with the parallel loader. So it's a Java utility. So I just I first show you and verify my properties file. So I'm loading the patient CSV file. I tell it what the columns are. You can also let it infer the column names from the file, obviously. And then I'm going to load this into my master table. You can let this one create the table if you need to. Or you can, well, in our case, we created it up front to show you how that works from Atelier. And if I now so this is again P equals patient properties. So in here it starts triggering a couple of processes and adding my 100,000 records with a pretty nice insertion rate in just a very short amount of time. So now I can see that my data is nicely evenly spread across my 6 nodes. So now if I want to add another, if I want to scale my cluster out, because oh my gosh, there's so much data in here. Sorry?
Why did each node have the same row count?
Oh, because it's randomizing, it's round robining, and sometimes it just jumps across one. It's randomizing the choice of which shard it goes to for every record. So
is the whole table then the sum of those rows?
Yep.
Okay.
Yep, exactly. So, and now if I can add another. So I can add another shard to it. There we go. So now if I go and look at my sharded table again, you'll see that this one has zero data. So now we want to do something about that. More specifically, I want to load a second set of patients, so about the same size. So it should take about the same time. So when I added my new shard, it didn't rebalance anything automatically. So we deliberately. Yep, that's exactly what I was going to show. So there you go. So it balanced the new data across the shards. So it uses the same round robin mechanism intentionally, because we don't want to put additional pressure on our new 7th shard, because that would slow down the entire process if you focus all of the data in that one to catch up. So that's why rebalancing really is a maintenance task. So that's also why we think it's fine to stick to an offline version in the initial case. So let's try and show you what that looks like. So, and this is where I hope we're going to get somewhere, because, so maybe I'm going to, as a fallback, already show you a couple of other tables that I created up front. So this is another table that has some data and didn't have data for shards 6 and 7. So I'm trying to kind of cover my ass already up front. This is something that we'll be releasing next year. So it's not meant to be ready for production use yet. But I think it's important to show, because it really is sort of the rebalancing thing is kind of the closing lid on this of this architecture that really brings this elasticity. So I'm going to ask it to spend at most 1 minute or second and give me a little report. And then the little report, well, this is hardcore, but anyway, so here I can see that it started moving some buckets around. So this is what I was afraid of, that my patient table didn't do what it was supposed to. But for the ST1 and STK1 tables, it already started moving a couple of buckets. And if I call it again, it will just have more. It will have moved the next set of buckets. And here I can see this in. Yeah, that's. Don't look. No. Please don't look. So here you might have seen that it should have. There you go. Here it started doing some rebalancing work. I might want to run that again, just so you see a little bit of. So typically you would let this run for more than just 1 second, but then eventually I should be able to see that there's even more records that have moved ship, have jumped ship to the other ones. So maybe also interesting to note here is that here, so these are 2 tables that are co-sharded, and these are also 2 tables that are co-sharded. So when it moves buckets, it makes sure, obviously, to move buckets for all the tables that are in one co-sharding group together at the same time, so that it just makes sense, of course. So that was a demo that still worked reasonably well. But again, so this is a work in progress. But we have sort of the proof points that we can do the rebalancing fine, and it actually runs pretty fast if it needs to. So wrapping up, it's important to not get too hooked up on this whole scalability thing. And oh yeah, let's add shards, and then everything will go faster. Yes, sharding is very powerful in a lot of interesting scenarios, but not all scenarios. So for example, Ted already called out very transaction-heavy scenarios. That's not what we built sharding for. Sharding is for distributing complex query workloads, mostly select and ingest and pure inserts, and that works fine. But apart from that scalability part, we're also investing a lot in performance, in SQL performance by itself. So this is these are numbers from a workload that we got from a customer. So it's a real-world workload that we ran on the exact same hardware on 2017.2, 2018.2, and then the builds that I was also using, which is an alpha build of 2019.1. The exact same data set, exact same queries, and you can see that it went almost 35% faster, just because of all of the wonderful things we're doing on the SQL side. So we've put a lot of optimizations in the query optimizer, in the generated code, etc. I'd be happy to talk to you more about those things, but I'm already getting a little over time, so I'll stop here. And then if you have more questions, we can talk about that in the Tech Exchange, or we can talk to the developers if you haven't talked to them already. So just to close off, why is our horizontal scaling architecture really differentiating against the competition. So the performance. As Carlos pointed out, we can beat in-memory databases on their home turf. They had all of the data that they could fit in memory because they were treating less data. They had it all in memory, and still we were able to beat them on performance. Flexibility of modeling. We're very well aware that the 18.1 and 18.2 releases only support SQL, but we are in the process and getting close to supporting other data models as well. So that is, and the schema flexibility that you have with InterSystems IRIS is also something that's pretty powerful. And of course, it's only one part of the platform. We don't need to put Redis or times 10 or grid gain in front of the data store to provide to you these low latencies with that caching layer. No, it's also InterSystems IRIS instances that were in the compute layer, whereas other solutions will use third-party technology. So 100% homogeneous architecture that can give you this as one single platform. With that, any questions? Yeah. Yes.
And then that all gets built back together again.
Mm-hmm.
So there's each one would have its own cache, or not cache, but its own data set,
Mm-hmm.
and with its own unique set of rows that's in it, and then those get just kind of built back together.
Yeah, we're horizontally partitioning the data, so indeed in buckets of rows that go into the different data nodes. For this demo, I tweaked things a little bit to have small bucket sizes so that I could show something, because by default, it's kind of blocks of 250K records. So you need a lot of those to start moving buckets around. But yes. So what nodes will do is, if a data node gets, if you connect to one data node and you issue a query, that data node will kind of will examine the query and send shard local queries, so the ones that can run in isolation on the individual partitions. It will send those to all of the other nodes. The other nodes will resolve those queries, pass those queries back to the querying node, and assemble the results there and kind of do the additional processing that might still be required. So for example, if you do a select count on your table, it will do select count on every individual node, and then the combination query, so to say, is just adding up those counts. So that still happens on the node where you connected to initially. And so that's also why you want to load balance your user connections across the entirety of your cluster. Okay, with that, I think it's about time to head back to the main conference room for the last part of today. These are a couple of other interesting sessions that relate to this. If you have questions, or if you the ones that are in the past already, you can see the recordings for those coming up shortly on learningservices.com, learning.intersystems.com, and we're around if you have questions. Thank you.